So this talk is about computational building blocks for machine learning on graphs. So I think most of us should know what is a graph, but let me define it first. A graph is a representation of data. So any relational data, for example, if you represent relationship between entities, that can be concisely modeled as a graph. And in different scientific domains, they can mean different things. For example, if we talk about biology, like how protein interacts in our body, then that can be represented as a graph where entities are proteins represented by vertices, and then their relationships are represented by the connections or edges. If we think about social network, then different individuals, they represent vertices, and friendships can be represented by edges. If we think about our brain, that can be modeled as a big graph where neurons can represent vertices, and then neuron interaction like neuron synapses, they can be represented by edges. So in that sense, graph is an abstract mathematical model that can concisely capture relational data. There are many applications. For example, if I think about Facebook, a big social network, that can be modeled as a graph. And this is a reasonably big graph because Facebook has more than 2.2 billion active users. And given this type of graph, we often would like to learn how information spread, how to recommend friends, and how to advertise, targeting different individuals. So those type of high-level learning tasks that we do on social networks. Similarly, if I think about a different type of network, like our brain, this is also can be modeled as a big graph. Our brain has more than 100 billion neurons and 100 trillion synapses. And if we can model this as a graph, then we can try to understand how brain functions, how to diagnose and treat different diseases, and so on. So once we map our data to this abstract model called graph, then typically when we learn on top of this data structure, there are many different learning objectives that we often formulate. For example, we'd like to classify nodes in a graph, or classify a subgraph or the entire graph. For example, in protein network, we would like to classify proteins, or in topic network, we'd like to classify topics, and so on. So given a graph, we may want to predict links. That is another learning objective. For example, if this is a social network, can we predict whether two nodes, X and Y, will they be friends in future? And based on this, we can recommend friendships. We often try to identify communities. And of course, we'd like to visualize a graph in 2D or 3D plan. So those are common learning objectives that we typically do on graphs. So based on this brief introduction, in this talk, I have 5 clear objectives. So at first, I'll discuss when we learn on graph, what do we need primarily? And I argue that we typically need graph embedding. We'd like to embed a graph into a low-dimensional Euclidean space. I'll discuss different types of embeddings, mostly shallow and deep embedding. Then, if we agree that graph embedding is perhaps the most important operation in graph learning, then I'll discuss the computational pattern, main computational pattern in graph embedding. And I will argue that message passing messages between or among different vertices is the main computations in graph embedding algorithms. Then I will discuss if we consider message passing as the primary computation in graph embedding algorithms, what are those computations? And then I will discuss 2 linear algebra operations, multiplying a sparse matrix by a dense matrix called SpMM, and multiplying two dense matrices sampled by another sparse matrix called SDDMM. Those are two computational kernels that we need in almost any message passing based graph learning algorithm. I will give three examples: graph drawing, graph embedding, and graph neural network. If we agree that those are key computations that we do in graph machine learning, then I'll discuss how can we make them efficient. And in graph analytics or any sparse data analytics, memory is everything. I'll discuss how can we optimize memory utilization for those computational kernels. And finally, if we implement those kernels very efficiently on one particular architecture, for example, we develop algorithm for Intel processors, can we make this portable? How can we run the same algorithm without losing any performance to another architecture like ARM or AMD processors or even GPUs? Then I'll discuss a simple auto-tuning framework where we don't need to change our code. The tuning framework will generate optimized code for different architectures, and then you can run the same code by tuning to different architecture, and you can still get very good performance. So I have these 5 sections in my talk. I discuss how can we map graph learning algorithm to graph embedding, then discuss message passing framework for graph embedding algorithms, then computational kernels, SpMM and SDDMM, two linear algebra operation that we use in message passing framework. And then I'll discuss how to develop efficient algorithm for those linear algebra kernels and how can we make them portable. So let us begin with general learning on a graph. And I would like to pitch this idea that no matter what you do, most often we need graph embedding. So suppose here is a very simple learning task. We consider a network where we have two different types of nodes, human or bot. We have only 6 nodes in this graph, and for 5 nodes we know whether the particular node is human or a bot. And for the last node, we are asking the question, can you predict whether this is a human or a bot? So if you think about this problem, this is a simple binary classification problem. Given a node, we have to classify, and that is a binary classification. Before we develop any fancy algorithm, we may simply ask, can we apply a traditional machine learning algorithm such as logistic regression to solve this problem? What could be the problem there, or it can be done or not? Now, if I think about the data itself, so if I think about a graph, and a graph can be represented by an adjacency matrix like this, where if there is, if I have 6 nodes, I'm talking about a 6 by 6 matrix. And if 2 nodes are connected by an edge, I put 1 there. And if they are not connected, I put 0. This is simple binary representation of the original graph. Now, if I ask this question, what is the dimension of this graph? And we can get some idea from the matrix. So in that matrix, every row represents the connectivity pattern for a vertex. So first to represent the connectivity pattern for vertex 0, and so on. And in any data view of a matrix, we can often think each row represent individual data item and each column represent features. So in that sense, this graph is 6-dimensional because we have 6 columns. So according to a long-standing definition from Ardosh and his colleagues, given a graph with n nodes or n vertices, the dimensionality of the graph is n. And if we talk about a graph with 1 billion nodes, that means the dimensionality of the data is 1 billion. And because of this high dimensionality, we often cannot use traditional machine learning approaches such as logistic regression. It's very hard. And also, we need enormous amount of training data to learn from this type of high dimensional space. So to solve this problem, what we do is we embed one node into low dimensional vector space. So for example, here, this node U, we embed the node into D dimensional vector space, where D is much smaller than N. For example, D can be 126, where number of nodes in the graph can be 1 billion. We'd like to reduce the dimensionality of the graph. The graph is represented by an n by n matrix, where n is the number of vertices. From this, after we embed the graph into D dimensional space, we'll get an n by D matrix. And that is a latent space, but we're reducing the dimensionality significantly. This thing is called graph embedding. After we embed the graph into low dimensional space, then we can solve many problems by using standard machine learning approaches. We can cluster, we can classify, for example, we can apply kemels algorithm to cluster nodes. We can use logistic regression to classify nodes and so on. So because of this, node embedding or graph embedding in general is the most important concept in graph-based learning. We embed node, what is the learning objective there? How should we embed into low dimensional space? So when you do so, we think about a function. We think about a magic function f. So given this magic function will embed the graph into a low dimensional, in this case, 2-dimensional space, so that if we have two nodes that are similar in the original graph, in some quote unquote similar, that means it depends on the application. If they are similar in the original graph, after we embed them, they should be placed close to one another in the embedding space. For example, here, if we say two red nodes in the original graph, they are from the same class. Then after we embed them in the embedding space, they should be placed close to one another. And in graph embedding, our goal is to develop a good function, f, this embedding function. So more specifically, what we want is for every vertex, we would like to develop a function called encoder. To encode a vertex, the encoder will take the vertex as input and will return a d-dimensional vector. Now, for U, this d-dimensional vector is called ZU. And our objective is, after we embed those nodes into our d-dimensional space, then we can compute the similarities. So suppose we have two nodes, U and V, we embed d vector space and we got their embedding as ZU and ZV. If we compute the similarity after we embed them, for example, if you compute the similarity by using dot product, what you want is their similarity in the embedding space, similarity in the original graph space. So what we're saying is, after we encode those vertices into our Euclidean space, and then if we define the similarity in the Euclidean space by the dot product of these two vectors, and if we also define the similarity of these two vertex U and V in the original graph by some notion of similarity, I'm not saying what should be it, but maybe if they are connected, that is one notion of similarity in the original graph. The similarity in the original graph and similarity in the vector space, they should be related. And that is the general purpose goal of graph embedding. So in graph embedding algorithms, we have two components. One is called encoder. That means given a vertex, we have to encode the vertex by a vector in d-dimensional space. And we need to define that in any algorithm. And then we have to define the similarity function. how can we define similarity both in the embedding space, also in the original graph? So here, this term similar U and V, they define how two vertices are similar in the original graph. For example, one simple notion can be if there is an edge between U and V, then they are similar. That is a valid definition. It can be something else as well. And when you embed them into embedding space, then we have two vectors, ZU and ZV. What is the similarity in the embedding space? In this case, I'm defining them using dot product. We have to design them. We define graph embedding algorithms. And after we define them, this is a typical learning flow. So we have some magic function, encoding function. For every pair of vertices, we can encode them, and then we get d-dimension. And then we can decode them. Here I'm using a pairwise decoder. That is nothing but computing their similarity. For example, it can be their dot product. Then, based on this similarity in the embedding space, and based on their similarity, S, G, V, I, V, Z represent their similarity in the original graph, we can compute a loss function. If they satisfy one another, then the value of the loss function should be small. If they differ, for example, if two vertices are connected, but they are placed far from one another in the embedding space, then the value of the loss function should be high. And we have to minimize the loss function and update the embedding. This is a typical workflow of most graph embedding algorithms. And how we encode them. So here is, I put a bar here. It can change from another. This is a brief table of graph embedding, but this bar, typically, state of the art, we have two approaches. One is called shallow embedding. A shallow embedding is nothing but an embedding table. So for every vertex, we have a d-dimensional vector, and that is stored in a table. For example, for vertex I, we have a column in this table. And whenever we encode a vertex, we simply look up the table and then pull up the vector, and that is my encoding. And in my algorithm, I reiterate and update this embedding table. This is often called shallow encoding, just table lookup. And in recent years, this encoding can be designed using deeper neural network. So we can place multiple neural networks, multiple layers, use normal activation functions and so on. I'll discuss few of them later. And then we get an embedding out of it. So instead of looking up a table, we can have a complicated multi-layer neural network in between, and that can give us the embedding, the encoder function. And after we embed them, remember we have to decode it to update network parameters. So that is the second step. But the encoding can be shallow or deep. So far, what I have discussed is graph is a very high dimensional data, and without embedding a graph into low dimensional space, it is very hard to learn efficiently. That is why graph embedding is perhaps the most important and interesting operation that we do in graph machine learning. And in graph embedding, we have to encode vertices into low dimensional space. So we need an encoder, and that encoder can be a shallow encoder or a deep encoder. So that is how I'm motivating you that maybe we should focus more on graph embedding algorithms, and that will be the next part of my talk. Do you have any question here? Okay, so moving on. So if we assume that graph embedding is the most important operation that we do in graph learning, So what is the main computational pattern in graph embedding? Using one slide that I discussed already, when we embed a graph into low-dimensional vector space, we have an encoder function where we encode a node to a vector ZU. For node U, we encode this to a d-dimensional vector ZU, and same for another node. We also do similar stuff in images. So let us take a look at images first, because images are simpler. And most of us may know about this. So in images, suppose if you'd like to detect the image of a bird, if you'd like to classify the image of a bird, what we typically do is we try to identify features. If you are trying to identify beak of a bird, we place a small filter there. And then we compute the dot, we consider an image convolution operation. For the filter and for that part of the bird, we compute the dot product, sum them up, apply a nonlinear transformation, and they get one output out of it. For another bird, we slide that filter across the image, for example here, and then we can get another value for this. So in images, we put small filter that is a fixed size filter, dense filter, that means typical, that is a dense matrix, small dense matrix, and then we slide that filter across the image to identify different features. The same idea is also applicable on graphs, but the concept is a bit different here. So in the left part here, I'm talking about a filter, 3x3 filter. And what I am doing here is I'm representing pixel as a node in a graph, and I'm connecting adjacent pixels by edges. So in that sense, an image is nothing but a regular graph. And when we apply a filter, here I'm put this blue square 3x3 filter. We slide that filter in the image and identify different features. And that is a part of image convolution or convolutional neural network. That is easy in the sense that this filter is dense and this is regular, images are regular. In graph, we can apply similar concept here. For vertex 2, I am applying a filter shown by this blue part. But this filter is not dense anymore because vertex 2 is not connected to everybody else. And it is irregular because the filter that I'm using at vertex 2 will be different if I apply this to vertex 5. So we tackle this by using a message passing framework. That means if we are considering vertex 2, we have 3 neighbors, 1, 7, and 3. They will send some messages to vertex 2, and based on these messages, vertex 2 will compute the signal, or we often call this activation or whatnot. So key point here is in graph embedding or graph convolution, whatever you call it, whenever we consider, here I am giving a simple example. Suppose we are talking about vertex U, and we'd like to compute the embedding of vertex U. This can be done by a 2-step process. In step 1, for all edges adjacent to U, we compute messages. For example, for this particular edge from V to U, we'd like to compute the message, and I denote that message by HUV. UV denote the edge. And that is a function of 3 things. One is the vertex feature for vertex U, the feature of vertex V, and if we have any weight or any feature on that edge, that is also considered, which is AUV. So I'm packaging everything, like when we generate a message by using a single function psi. And we do this for every edge in the graph. The actual value of the function is user defined, and it can change from one algorithm to another. But I'm just discussing the computational pattern that we see in message passing based algorithms. After we generate the message for every edge, we aggregate this message in this particular vertex U. So if I have three neighbors, for vertex U have three neighbors, which is defined by NU, then I loop over those three neighbors. That means I consider all those three edges where you have already generated messages. We aggregate them, maybe we sum them, we compute max, mean, what not. Just an aggregation function, and then we get a new embedding for vertex U. This is a typical pattern in message passing based embedding. We generate messages for every edge, and then we aggregate them to get new embedding. We repeat these steps many times based on our learning objective and loss function. And these three functions, phi, psi, and this aggregator, they are user-defined algorithm specific. But the computational pattern will remain the same. So let me show you a couple of examples. This is a generic framework. I'm not saying which algorithm we are using, but we can consider a particular example, suppose graph convolution. Graph convolution was a particular example, and in that algorithm, when we generate messages, for example, if we generate messages in this particular edge V and U, it does nothing. That means okay, I made a mistake here. It should be XV. That means when we generate messages, we simply pass the information from vertex V to this particular edge. That means messages are directly copying the vertex information or vertex vector for the neighbor. That is part of graph convolution network. Message generation is easy. Just copy that value here. And then after we generate the messages, the message aggregation is simply summing them up and then applying a nonlinear function. I'm not discussing that, but graph convolution network is very easy, passing information from neighbor on the edges and then summing them up. So it falls into the pattern that I discussed before, message generation and then message aggregation. Similarly, in typical graph embedding algorithm, what we do whenever we generate messages, we consider the dot product of their embedding. If we consider this particular edge U and V, we compute the dot product and then apply a sigmoid function or any nonlinear function, and that will be the message for the particular edge. And again, this can be written in this formula, where psi is our function, which is dot product followed by the sigmoid. And after we generate the messages, we again aggregate. And the aggregation function can change. For most graph embedding algorithm, it is after you generate the message, which is HUV, we consider element-wise dot product with the neighboring vector and then sum it up. And once again, you can write in this generic formula. Similarly, we can develop complex graph neural networks where the message generation can be done by multi-layer perceptron like this. So it can go over smaller individual neural network per edge neural network. But no matter what you do, that can be captured by this computational pattern, a function psi that will take the embedding of V and U and do whatever it likes and give us edge-wise messages. And then we can combine them by using our aggregator, which can be max if I use max pooling or whatnot. So long story short, what we're saying is no matter how we embed, it can be captured by a message passing framework that has two steps, message generation for every edge, and then aggregate those messages in vertices. And most graph learning systems, for example, PyTorch geometric or deep graph library, they have a message passing app for developing graph machine learning algorithms. Because of this, because you can just aggregate messages and then using this API, you can implement almost all graph machine learning algorithms. So that was my part 2. That means I'm saying graph embedding for most all graph machine learning algorithms, and then we can use a message passing interface or message passing system to develop any graph embedding algorithms. Any questions so far? Okay. I'm moving on, but if you have any question, please interrupt me anytime. So, convinced that we are using message passing interface for graph embedding, then what are the main computational kernel in graph embedding? And would like to do this in bulk synchronous fashion, because, for example, here, if we just generate message for every edge, it will be hard to manage. So even though high-level interface is message passing interface, but in the low level, we don't want to do this. We would like to do this using some linear algebra operation. Linear algebra operation that we can use. So here is, again, considering the left side, I am showing a graph with 8 vertices. And for now, let us consider this vertex, vertex 1. How can we generate messages and then aggregate messages to get a new embedding of vertex 1? So in the previous few slides, I discussed we have to generate messages. That means H12, H14, and H18 for all 3 neighbors, for all 3 adjacent edges for V1. And this can be easily captured by this notation, Chi x1, x2, and A12, where x1 is the current embedding of V1, x2 is the current embedding of V2, and A12 is some edge information. If it is binary, we can ignore that. So this operation, this figure may look complicated, I can explain that, but this operation can be mapped in this way. Suppose, remember that this function psi, it depends on x1 embedding for this particular edge. It will depend on current embedding of 2 endpoints and any edge value. So suppose we're talking about this edge V1, V2. That means we have to consider, and I represent each row here, represent the current embedding of those vertices. And for neighbors, I'm using a different notation Y for generality, but in many cases, this can be simply X. And I'm considering only 4 vertices here because in most machine learning, we consider a mini batch. That means a batch of vertices that are updated simultaneously. So I'm only considering 4 vertices out of 8 vertices in the original graph. Okay, so when I consider all messages for vertex 1, that means we need to consider 3 messages. So for this one, as V1, V2, we have a vector x1 representing the current embedding of V1. And I'm saying for V2, I'm representing this by another vector y2. And in this case, I'm considering 3-dimensional embedding. And they are guided by this non-zero entry. So if there is any edge, I'm showing them by these dark colors. We consider these 3 vectors, and it can be a simple number. We consider them, apply a function psi, and then we get edge-wise message for edge 1 and 2, which I represent by this term H1. For 1 and 4, I do the same. We take the same vector. We consider y4, which is the current embedding of vertex 4. And then this is my any edge information tab that is represented by this part matrix. and then we apply our function, and then we get another message for edge 1 and 4, and similarly for 1 and 8. For the second vertex, if we have another vertex x2, we do the same, following those non-zero patterns, and then get our output. So if I think about this operation is called, in linear algebra term, this is called sampled dense matrix multiplication. What we are doing here is we have a dense matrix and another dense embedding matrix. Remember that they can be the same. In many applications, they are actually same. X and Y, they represent the same matrix, but in other applications, they can be different. For example, if we are talking about bipartite graph, they can be different. So we are essentially multiplying two dense matrices guided by another sparse matrix. And this can be written in this way. We multiply two dense matrices, X times Y transpose, and then element-wise multiplication with A. And it means that if there is any zero entry in our sparse matrix, we don't need to compute the corresponding entry. And this can be captured here. We only compute where we have a non-zero entry here. This operation is called sampled dense matrix multiplication. And we can apply this multiplication to generate messages for every edge in the graph. And the input of this operation is two dense matrices and another sparse matrix. Output is another sparse matrix. And the sparsity pattern of the output matrix is exactly same as your input sparse matrix. And for every location of the output, it can be a single number, it can be a vector, or it can be anything. We have no control over it. It is application dependent. Here I'm showing them as a vector. So after this operation, we are generating messages for every edges in the graph. Then we have to aggregate them. So suppose we generated messages for every edge, and remember that here I am using dark locations to denote edges. So we have messages H1 to H1. Then we apply aggregation, and in aggregation we can also again consider embedding vectors for neighbors. We apply another function phi, and then we sum them. It can be any aggregator, and then we get the new value, new updated embedding for vertex 1. Here, what we are doing is we are considering a dense matrix Y and a sparse matrix H. We are multiplying them and aggregating them. That is nothing but a sparse matrix dense matrix multiplication. So in summary, we can consider the message generation and message passing algorithm. We can consciously map them to this two linear algebra operation. And the previous one was SDDMM, and this one is SpMM, sparse matrix dense matrix multiplication. So if we know how to implement these two operations efficiently, then we are saying we can implement any message passing algorithm, and that means we can implement any graph embedding and graph neural network algorithm. Then we also observed that if we generate messages and then immediately aggregate this, we don't need these two operations. We don't need two separate operations. Instead, what we can do, whenever we generate those messages, we can aggregate them immediately. And based on this observation, we developed a new kernel called FusedMM, which is nothing but fusion of SDDMM and SpMM. We generate messages and then aggregate immediately instead of storing them in memory. It can save memory as well as lots of memory traffic, and it can make, we can easily faster algorithm if we get output. In that part, I was discussing whenever we want to implement message passing based graph machine learning algorithm, we just need two operations. One is sampled dense matrix multiplication, and there is sparse matrix times dense matrix multiplication. We can even fuse them by capturing everything using a single kernel called FusedMM. And if we know how to efficiently implement this, then we know how to implement graph neural network, graph embedding, and all other algorithms by using just one or two kernels. Any question?
Yeah, I have a question. So why were those separated in the first place? Is that something that's done in general graph frameworks? Or, because I would just write it that way if I were to write from scratch.
Well, so I believe those operations are there before we discovered that we can use them to develop graph machine learning algorithms.
Mm-hmm. Oh, I see what you mean.
Yeah. And we are now discovering that maybe we don't need them. We don't need separate operations.
Okay. Thanks.
It is like BLAS operations. So people defined those operations first and then discussing how can we use them to develop graph algorithms. Now,
right, that makes sense.
Yeah, if we start from graph algorithms, then maybe now we are saying, okay, we don't need them. Maybe we can squeeze everything together by a single operation.
Mm-hmm. Thanks.
Okay, by the way, I did not mention one thing. In recent attention-based algorithms, suppose you need to store edge-wise messages. In many applications, we may need them. For example, if you are using attention mechanism for every edge, then you have to store edge-wise messages. In that case, you cannot fuse them.
Sorry, why is that the case?
Well, in graph embedding, what we need, our ultimate output is one vector per vertex.
Right.
Some cases, in some neural network, we also output some information for every edge.
Mm-hmm.
If that is the case, then you cannot fuse these two operations because you need edge-wise information as well. You cannot discard it. You have to store it.
Oh, I see what you're saying. Okay, yeah. Got it. So this is more like convolutional. Okay, got it. Thank you.
And any other question? If we're talking about those two operations, or maybe their fusion, how can we make efficient implementation of them? And I'm saying we just have to consider memory utilization and maybe load balancing. We don't need to consider about CPU performance at all. First thing is about memory. So if I can fuse them, in most cases, yes, I can, then we can save significant memory. As if we have separate operations like SDDMM, edge-wise message generation, and then aggregation, then our memory requirement can be order of number of edges times D, where D is the embedding size and it is number of edges. If we have vector messages, and it can consume significant amount of memory. Here is one particular example. Here DZL represent deep graph library, and they have these separate kernels. And FusedMM is their fusion, and we can see that when your embedding dimension increases, the memory requirement of this fused operation does not change because you are not storing messages. But if you have to store messages, then it can increase significantly. That is one aspect of memory requirement. But there is another aspect, and that is we know that graph algorithms, most graph algorithms, also graph machine learning algorithms, they are memory bound. And one way to verify this is by a roofline model. A roofline model where we have operational intensity on the x-axis. That means for every floating point operation, how how many bytes you have to read from memory. That ratio is represented by operational intensity. So if, for example, if we multiply a sparse matrix by a dense vector, SpMV, the operational intensity for that operation is 1/4. And if that is the operational intensity, then there is no way that you can reach the peak performance of any processor. And the roof line plot says that this roof line here is determined by the memory bandwidth. So whenever you hit the roof, you follow the horizontal line and maybe say this 32 gigaflops per second is the best performance that you can get for this given hardware. And everything at that point, your performance is bound by your memory bandwidth. When we try that model for our operations, FusedMM, then our operational intensity was like that, where delta is your average degree in the graph and D is your embedding size. If I plug some simple standard values, for example, your average degree of the graph is 16 and embedding size is 128, this value is close to 1. And we know that for most hardware, if we would like to read 1 byte from memory for one floating point operation, then it is definitely memory bound because memory access is slow. So how can we optimize memory accesses? We'd like to utilize memory bandwidth efficiently. That means we want to stream data. And we would like to use temporal locality. That means whenever we read something from memory to our cache or maybe register, we'd like to use it as much as possible. We do everything, we have to consider thread level parallelization, and we adopt a very simple strategy. That means one-dimensional partitioning of the data. Suppose we have 3 threads. We consider this is our input X, another dense vector Y. This is our sparse matrix A, and this is our dense embedding Z output. We partition A, X, and Z horizontally so that we have approximately same number of non-zero in each partition for the sparse matrix. And then each thread can multiply, for example, thread 1 will consider this red part of X, red part of A, red part of Z, and whole Y sequentially within that particular thread. That means we never read X, A, and Z more than once. We may have to read Y more than once. Then within a particular thread, we want to make sure that we don't read data more than once unnecessarily. And we make sure this by using register blocking. Suppose we are considering a very simple register of length 2. That means we can only store 2 entries in the register. Then what we can do, in order to multiply this part of Y with our X, we can allocate 4 registers, 2 for X and 2 for Y. We put the data into register, and we also allocate 2 registers for our output Z. And remember, when we generate messages for every edge, for this particular edge, U2, 3, we have to compute some operation between these 2 vectors. Suppose we are computing the dot product in graph embedding algorithms. Then for given these 2 vectors, we compute the dot product. Maybe we can apply a sigmoid function, a nonlinear function, and then we get one number. So this is the message for this particular edge, U3. Then we can partially aggregate this with the result. That is message. This is not full message aggregation. This is partial message aggregation for this particular edge. And then similarly, we can do the same operation for, for this edge, UN5. The benefit of this approach is we load X and Z into register, and we don't need to reload them again. We stream over Y and load necessary entries to registers and then perform our operation. So this can give us maximum utilization of temporal locality. So register blocking is done within each thread, and it works perfectly fine as long as all data fits in register. When I say all data, I mean only neighboring information for a given vertex. If we can store the embedding of that vertex and the output and some part of neighbors, that is enough. And in many cases, we can do that. If we plug, when we measure the performance on an Intel Skylake machine with 100 GB per second bandwidth, we see that our performance is not still optimal because this is the peak bandwidth line. And if everything is optimum, we should have hit this line. But our performance for different graphs or code YouTubes, they're different graphs. It's slightly below that line. And we speculate that this is because we're calling everything from a Python interface. Code is written in C++, but we're calling everything from Python interface. And this Python to C++ conversion may be eating up some performance there. But still, we are happy with this performance because it is very close to the peak performance that we can get. For example, in some cases, we are getting around 60 gigaflops per second, which is much better than what we have observed in standard libraries. Then we compare the performance with a state-of-the-art library called Deep Graph Library, where the backend is C++ and frontend is based on PyTorch. And that library uses separate SDDMM and SpMM. And then what we observed when we run this code on Intel Skylake server on 48 cores, in Deep Graph Library, they use separate SDDMM and SpMM. If we just use fused at the FusedMM without any optimization, like we discussed about register blocking and other stuff, we can still get 2x performance improvement because we don't store intermediate results in graph embedding algorithms. And if we apply all those optimization, then we can get another 5x speed up, so total 10x speed up. For other type of application like graph drawing application, we can get different speed up. For example, just no optimization, if we can apply this fused operation, we can get 6x speed up and then another 5x from operation. And this is because in graph drawing, we have to store vectors, and memory traffic would be much higher in that application if we would like to store edgewise messages. And similarly, for graph convolution, we see similar trend. So fusing operations and then optimizing the operation will almost always about an order of magnitude performance with respect to state-of-the-art library. Then we discussed about how can you ensure portability. Like if we, this performance was at Intel, if we'd like to run this on ARM, IBM, or AMD processors, what we have to do. Then we took the philosophy from a popular package called Atlas in linear algebra, where they have a code generator, and you can generate different single instruction multiple data code for different architectures without changing your underlying code. We incorporate this type of framework and then easily automatically develop code for ARM and AMD processors. For example, when we apply graph convolutions on AMD and ARM, we can still see that the fusion operation can give us significant performance improvement. We obtain better performance on ARM. For example, sometimes it is 18x faster than standard library. And similar, we observe similar performance improvement for graph drawing and graph embedding algorithms. And so far, I only discussed about the kernel part of that. So when we consider FusedMM or SDDMM plus SpMM, I discussed about the actual timing of that kernel measured from Python interface. But when you consider end-to-end performance, like if I run a full graph embedding algorithm, then we can still see that the performance improvement when you use FusedMM is sometimes 25x faster than deep graph library. And if I write everything from scratch in PyTorch, then it can be even worse. Like PyTorch is slow, deep graph library improved some of them, but by fusing operations and then optimizing them, we can get significant speed up, sometimes 45x speed up with respect to PyTorch. So going forward, that is what we developed recently, shared memory performance improvement. We'd like to implement everything in distributed memory. And what we have to do is this operation, this single sparse matrix, dense matrix multiplication and dense multiplication. We just have to split the matrices. This is the matrix across multiple processors. And then each processor can compute their operation independently using all the algorithms that we had discussed. So just to summarize, what we discussed is whenever we learn on graph, the most important operation is graph embedding. And computational pattern in graph embedding can be captured by message passing among vertices. And message passing system can be implemented by two operations, sparse-dense multiplication and dense multiplication, sample dense multiplication, and they can be fused together by FusedMM. And when we discuss about efficient computation, we have to optimize memory utilization. And we can easily make them portable by using auto-tuning framework. And we developed FusedMM and experimentally validated all these hypotheses. That means we can actually develop almost all graph neural network algorithm using just one operation. So I'd like to acknowledge Khaled and Majidul for their contribution in this work. And they are all from Indiana University. And thank you for your attention.
Thanks, Ariful. That was a great talk. Does anyone have any questions?
Yeah, I have a question. When you were introducing different instantiations of this message passing framework, so you mentioned, I guess this is your work in the ICDM paper.
Yes.
That kind of looks like attention. Can you explain, like, what's the advantage of that model? And
let me quickly go back. I mean, here?
The next, yeah, this one.
Okay, so what I'm saying here is when you're generating messages, here I'm using a dot product between the embedding and then a sigmoid function. This model is not uniform. That means in that paper, in our ICDM paper, we use this message generation algorithm for embedding. But if I discuss about another embedding algorithm, for example, DeepWalk or Not2Vec, more popular algorithm, they use a different strategy. Their function, their message generation function can be a bit different.
So yeah, my question is what motivated this choice? So to me, it looks a little bit like attention, except you're not normalizing. Is there any connection to attention, or what was the motivation for this? Is it better on certain classes of problems?
Oh, okay. Yeah, so the motivation for this work is this one mimics graph drawing algorithm, force directed graph drawing algorithms. So in that paper, our goal was to make sure whenever we embed them, it follows a force directed model. And our goal was to make sure that the visualization that we are getting from embedding should be better. That was our own objective. And that is why we use this type of message generation.
Okay. So this is for graph drawing?
Yes.
Okay.
Because okay, go ahead, please. If you have any question?
Oh no, I think that was just an.
Do we have any other questions for Ariful? I got something I wanted to ask. When you mentioned the automatic code generation, what's kind of, for the various architectures, what's kind of changing? What kind of gets adjusted or optimized when you do the automatic code generation?
So it's about, I think we have the person here who developed that code. It is all about how to vectorize. So for different architectures like x86 or ARM, their vectorization strategy and their vector length, they're different. In our code generation, that is our main target, how to optimize those things. And that can be done well ahead of time. We don't need to do this every time we run a code. We can do this once and then use the same code for different applications. And this is actually a widely used technique in dense linear algebra. Almost all libraries have something similar to this.
Thanks. Any other questions?
Yeah, so this is for CPUs. I don't know, do people use GPUs with sparse, like graphs or other sparse data sets? Is this something you can do there as well?
Yes, I mean, we are planning to implement something on GPU as well, but the difference, okay, yes, I mean, GPU is used for graph neural network as well, no doubt about that, but it is not as widely used as with CNN, for example, and primarily because computation here, we consider they're free. We don't care about them. It's all about memory bandwidth. GPU has much higher memory bandwidth, I know that, but you will not get significant performance boost by using GPU in graph neural network.
Why is that?
It is because, so GPU is giving us significantly more computational power over CPU, right? But in what I said is that is not important for graph operations because your arithmetic intensity, like for every operation, you need to read, let's say, 1 byte of data from memory, and that is your performance. That is your performance bottleneck.
Oh, sorry, you're saying like the memory access is too slow on GPUs? But I thought they have onboard memory.
Yeah, I mean, it is not slow, but I'm saying it is not as fast as the computation is.
Okay, so there's no real reason to do graph neural nets on GPUs as opposed to CPUs?
No, we do. Sorry, let me go and step back. Yeah, we do use GPU for graph neural network. And we will, of course, implement our code on GPU in near future.
Oh, sure. I mean, I guess this is just a general question. So, like for convolutional neural nets, like you said, you find that training these things on GPUs is much faster than CPUs. And so saying that's not the case for these graph neural nets?
Yeah, because of memory bandwidth. For example, the Intel processor that we considered here, it has more than, let's say, 100 gigabyte per second memory bandwidth. For a good GPU, we can get, let's say, 600 gigabyte per second. So 6x. But processor performance is more than 6x.
Right. Okay.
So this gap is 6x in memory. So you can get, in theory, you can get 6x faster performance on a GPU. But for CNN, I don't know how much. It should be more than 6x.
Oh, yeah. Yeah, it's a lot.
It's a lot, yeah.
Okay, thanks.
All right. Any other final questions?
I have a question.
Yes, please.
So the message passing thing that you said, that it improves the result and also helps us in the computations. So in terms of graphs that have not just one kinds of edges, if we have separate kind of edges, in that case, how much helpful is it? And what's the drawback of not using a message passing, or how does it actually improve that case? Thanks.
Okay, so message passing that is actually for our convenience. Nobody is asking us to use message passing. So maybe I put the framework in a wrong context. Message passing, I'm saying everything can be represented as a message passing API. But you can, of course, implement anything without considering that. Now, about your question, if you have different types of edges, you can easily still use message passing systems. And we have a very general purpose function there. So if I go back to that part, so I call this file. You can do whatever you want there. If you have multiple types of messages, and that is actually a user-defined function, how to generate messages. So if you have multiple types of edges, you can still process them separately, or you can combine them by providing your own function. It will not affect the API. API will allow user-defined functions.
Got it. Thanks.
Hey, any other questions? All right, so I'd like to thank the speaker one more time. Thank you for taking the time to give us an excellent talk. Hope everyone else has a good afternoon. Thank you.
Thank you very much.
Thanks,